Yes, now in the last lecture we have discussed about the p-n junction diode, or simply the p-n junction. We have seen that how a p-n junction is combined and the transfer of electrons and holes, or majority carriers and minority carriers flow will be there inside it. So in the today's lecture I am going to discuss about a diode, a simple diode. I will also discuss an LED, that is light emitting diode. In this LED I will take a special case of a 7-segment display. And third, I will take the case of a photodiode today. So let's first start with a diode. So this diode, as we know, conducts only in one direction and does not conduct in the other direction. If I simply draw this diode as a combination of a p and n type semiconductor, it will be like this. The symbol of this diode will be like this, where this arrow shows the direction of the current. It means if I see here the forward bias case, in the forward bias case there are holes, and in the n type we have electrons which will be moved towards this side. If p is connected with the positive and n with the negative, then can I say that holes will move towards the negative terminal and electrons will move to the positive terminal. So from here can I say that if this is my p and n type, then the direction of the current will be in the direction of the holes or opposite direction of the electron. So this will be my direction of, and so this arrow mark will show in the symbol me the direction of the current. Now we have seen here that this p-n junction width is there. p-n junction width was there, and this width act differently when we do the forward and the reverse biasing. So if I take an open circuit case, or when we are not applying any biasing across it, or open circuit case, then I have given you a formula that width of the p-n junction was given by W, which is equal to under the root of 2 epsilon s by q 1 by Na plus 1 by Nd into V naught. Now over here 2 is a constant, epsilon is the electrical permittivity, epsilon s is the electrical permittivity, of the material. Maybe if I am using here a silicon or a germanium, or I will write of material, right? And this epsilon s is equal to, this epsilon s over here can be written as epsilon naught into epsilon r. Epsilon naught value is already defined, that is the absolute permittivity of free space, which is equal to 8.854 into 10 raised to power minus 12 farad per meter. And epsilon r will depend upon the type of the material. If I take a germanium, its value is equal to 16, and if I take silicon, its value is equal to 11.7. We can find these values on the internet also, no need to remember all these things. So this is the value of the width. Now we know that in the forward bias case of a diode, in the forward bias case, this width reduces, and we can say that our diode starts conducting. Diode starts conducting. Right. Now when it has to conduct, definitely there will be a flow of the electrons or the holes, or simply the majority carriers. In the case of forward bias, we have the flow of majority carriers. Majority carriers, and that current is given by I is equal to, or if I write here the forward current, because it is the forward bias case, so it is IF equal to I naught e to the power of Vd upon eta Vt minus of R. So this is the value of the current, and it is given in the amperes. Now these are the two important formulas, that is the forward current formula and the width of the depletion region in the open circuit case. I have already discussed this width also. This Q is the charge, Na and Nd are the doping concentrations, because we are using here p and n type semiconductor, so definitely some doping has been done. So Na is the acceptor, or simply the p type doping, Nd is the donor, which is the n-type doping, and V naught is the contact potential. I given this formula also in the last lecture. This V naught is equal to, which is the contact potential, given by Vt natural log of Na Nd upon Ni square. Again, you can see here this Vt is the thermal voltage, which is constant at room temperature. Natural log of NaNd. NaNd is the doping concentration of the p and n-type material, and Ni is the intrinsic concentration of that material. For example, if I am using here silicon, so definitely there will be some intrinsic value or intrinsic concentration value of that of silicon of the material I will write here. So from here, can I say that once I have made a p and n-type semiconductor of any material, then that V naught will be fixed, because it is not going to depend on any other factor. Na is fixed once I have made a p-type semiconductor, Nd is fixed, and Ni is also fixed for the type of semiconductor. Now Vt is there, thermal voltage. Only this, due to this change in the temperature, I will find there will be change in the V naught, and V naught is called as the contact potential. So these are the few formulas. In maybe you can get some numericals related to it. In some of the exams they may ask that with the change in the temperature, should V naught change or not, right? So definitely with the change in the temperature, these values of V naught must change, because it is depending upon Vt. And second, as I said, this forward current If is equal to I naught e to the power Vd upon eta Vt. So over here you can also approximate this value for numerical purposes. You can say that this is equal to I naught into e to the power of Vd upon eta Vt. I can neglect this minus one part, because it is only multiplying with this I naught. If I look here, I naught is my leakage current. You know what is this leakage current? It is the minority current which is there in the reverse bias, and its value is very, very small. In the case of germanium, we normally take this value equal to in microamperes, and in the case of silicon we take it in the nanoamperes, right? So this is very small value. Then Vd is the forward voltage across the diode. It is the forward voltage across the diode. It means the voltage that has been applied across the diode. For example, if I take this diode and I apply a voltage across it, let this be the voltage with some resistor value across, then definitely this voltage will be divided across this resistor. I will write the voltage across this resistor is VR, and the voltage across this will be Vd, that is diode. So I am talking about this voltage over here. This Vd is there in it, is called as the forward bias voltage across the diode. Then we have eta, which is called as the recombination factor. The recombination factor, and in some of the books you may find it as utility factor also. So this is one and the same thing. So this eta is also different for different types of the materials. If I take the case of germanium, this value is equal to eta is equal to 1, and in the case of silicon, this eta is equal to 2. So depending upon the type of the material on which we are having, we have made a diode, we will substitute the value of eta. Vt is again a thermal voltage. Now with the help of these formulas we can calculate different values like forward current, width, or in the other way, width is given to us, they may ask us about the doping concentration, so these can be calculated. Now we have also seen that this diode is acting only in the forward bias, or it is conducting in the forward bias. So if I draw the characteristics once again, so the characteristics were like that. That is, in the forward case, the diode was conducting, only small amount of current is flowing up to a particular voltage, which was named there as the knee voltage in the last lecture, knee voltage, and exactly after the knee voltage we found an increase in the current like this. Similarly, in the reverse bias we have seen very small amount of current is flowing. It is due to the leakage current only, and that leakage current is the minority current, and after that, after a particular voltage called as the breakdown voltage, we find a very large increase in the current, but in the opposite direction. Now look here, in the forward bias case, this current is the majority current. or the majority carrier current, whereas in the reverse bias this current is due to the minority carrier current, minority carriers. Right. Now if we look at this majority and the minority carrier currents, I will draw a diagram over here for more better understanding. Now if I take this is my P side and this is my N side, in the P side I will take the negative ions. We have discussed this representation also, why we take negative ions on the P side and positive ions on the N side. And if I draw here the holes along with it and electrons. Now if I see here that if I do the forward biasing here, if I do the forward biasing, then what is going to happen? We have already discussed this part also. In the forward biasing, the P will be connected to positive and with the negative. Then look here, these holes will be higher concentration to lower concentration in the N side, and electrons are moving from higher concentration to lower concentration on the P side. So this is my diffusion current. Or I can say that in the forward bias, I have majority carrier current, or the current due to the majority carriers, and secondly I can say that this current is due to the diffusion. Similarly, if I take the reverse bias case, now if I reverse bias this, then due to the reverse bias P will be connected to negative and N with the positive. Now these majority carriers, definitely the holes in the P side and electrons in the N side cannot cross this barrier. But look at these electrons at the P side and the holes at the N side. Now these electrons at the P side will cross this junction because they will be attracted towards this positive. So they will cross here, and these holes from the N side will cross to the P side. Now look here, the electrons are moving from lower concentration in the P side towards the higher concentration in the N side. It means this current is called as the drift current. So I can say that in the reverse bias we have current due to minority carriers, and second I can say that this current is the drift current because they are now moving from lower concentration to the higher concentration. Right. Now next we have is the characteristics. We have done that. Now if I take the ideal case of a diode, in the ideal case, or if I take the first the practical circuit of a simple diode. So if I take the practical circuit or practical circuit of a diode, so I have taken here two cases. First is the forward bias and second is the reverse bias. So when I'm talking about a forward bias diode, so can I say that a normal diode which is represented like this, when it is forward biased, can I represent this diode with the resistor, with the help of a resistor and a voltage? Now look here, when this diode is forward biased, we have to overcome some voltage which we have discussed here, equal to the knee voltage. Right, so this knee voltage is the voltage which is obstructing the flow of the current. So it means if I connect this diode with positive over here and negative over here, it means this will be positive and this will be negative. So definitely this positive must be obstructed, or it must be opposed by some voltage. So I can name this voltage as my VR voltage, or simply the cut-in voltage or the knee voltage. Right, so this cut-in voltage values will be different for the different semiconductors. If I take the case of a germanium, it is 0.2 volt. If I take the case of silicon, it is 0.7 volts. Right, so this is the case of my forward bias. If I take the reverse bias case, then can I say in the reverse bias my diode does not conduct even after a proper voltage is applied across it. So it means it can be represented by a very large amount of resistance which is in the mega ohms. So I can represent it a resistance, maybe the reverse bias resistance, and this resistance is very large. It is very large, or you can say it is greater than mega ohm resistance, or is in mega ohms. Right, So this is the different practical circuits of a diode. When we implement a diode in a practical circuit, we consider this. So I can name this resistors as RF, the forward resistance, right? But we have a special case also, that is a ideal case. In ideal diode, what we have RF equal to 0, that is there is no forward resistance, and VR is also equal to 0. Similarly, the reverse resistance, it is equal to infinity. It means when I am taking the case of an ideal diode and I will forward bias it, so can I say the forward bias will be replaced by a resistance which is 0 and a voltage equal to 0, or simply it can be replaced with a short circuit. N is connected with positive and negative, or simply forward biasing. Or in the second case, when I will do the reverse biasing of this diode, in the reverse biasing, can I say it will be replaced by an infinite resistance? It means it will be open circuited, where P is connected with negative and N with the positive. So these are the few things that we will do while doing some numericals, or some in the numerical part. When we will have an ideal case or in practical case, we will make use of these concepts for solving our questions. Also, if I discuss the characteristics for of an ideal diode, then definitely my characteristics, if I draw it in the VI axis, V is here and I is here, then can I say the moment I have substituted a positive voltage or the forward bias voltage, there will be an infinite increase of current. So can I say my current will be like this, and similarly there will be no flow of current because of the open circuit in the reverse bias. Higher the value of it will be, so it will remain along the x-axis. So this will be my VI characteristics. If I draw it is minus V, right? VI characteristics of a ideal diode. Fine. Now next to it is a diode, is a light emitting diode. Now what is this light emitting diode? We have discussed this diode. In this diode we have seen that there will be the flow of current only in one direction, and which is given by IF is equal to I naught e to the power Vd upon eta Vt minus 1. Now second case, which is also you can see a special case of a normal diode, is called as a light emitting diode. Now what is this light emitting diode? Now this light emitting diode is nothing but a simple diode, which was also represented with a combination of a P and N type semiconductor. But the only difference is that it can emit light when there are recombination inside it. Definitely when we will connect it, or when we will forward bias it, P will be connected with the negative and N with the negative. P with positive and N with negative. Definitely the holes from the P side and the electrons from the N side will recombine inside because of this voltage applied over here. Due to this recombination, there will be the emission of light. Now this light may be in the visible region or may be in the invisible region, visible or invisible region, doesn't matter. It will depend upon the type of the material. In the earlier lecture we have discussed also a concept of direct band gap semiconductor. So what was that direct band gap semiconductor? I told you over there, direct band gap semiconductors are those semiconductors which are capable of emitting light when there are recombination inside it. And why that was occurring? Because the energy gap difference over there was such that when they are emitting light, they are emitting it in the visible region or in the non-visible region. So we have a formula which is related with the wavelength emitted by the or during after the recombination, or when the energy is released during the recombination. So it is lambda, it is equal to 1.24 by Eg. So if energy gap is in the visible region, you will find the wavelength to be in the visible, or if EG is such a way that the wavelength is in invisible region, we will have these types of light emitting diodes. So that's the reason we have few examples, like we have, if I say take a case of IR LED, which we find mostly in our remote controls or in many other applications. So this IR LED is fabricated with the material, normally we have gallium arsenide, for example. So it is fabricated with the material of gallium arsenide. Now if I take another, for example, we have different color LEDs like red, green LED. We have all seen, now these are very common. We have seen these LEDs, red, green, blue LEDs. So definitely these will be made of different materials whose energy gap is in such a way that lambda will lie in these regions. Fine. So this light emitting diode is nothing but a normal diode where the recombination which will occur during the forward bias case. Now look here, it is important. LED will work only in the forward bias, and if I do the reverse biasing, it will normally act as a simple diode or a normal diode. Means the normal diode characteristics will be there in the case of the light emitting diode also, or I will simply say it will not conduct, very small leakage current will be there, I naught. Now this, when it is forward biased, recombinations will be there, it will emit light. This is the difference between a normal diode and a light emitting diode. Fine. Now next to this is we are having a special case of a light emitting diode which is there in your syllabus, that is 7-segment display. 7-segment display. Now what is this 7-segment display? I guess some of you have seen this 7-segment displays. Now these 7-segment displays are nothing but combination of 7 LEDs like this. You might have seen this, and we normally name them as A, B, C, D, E, F and G. In some of the books you will find one more there, dot. So you will find there that is noted by H, but that is not important. We are concerned over here only with the 7 segments. So you can count 1, 2, 3, 4, 5, 6 and 7. So you will find these all 7 segments are nothing but the diodes in it, or simply the light emitting diodes, like this. Like. Fine. Now look here how these 7 segments are connected. It is important because we have 2 types of configurations here. If I take a common anode configuration, you know, common anode configuration, in the common anode we have, if I take a simple diode, in this diode this is my anode and this is my cathode. We all know, means the P side will be the anode and the N side will be my cathode. So if I take the common anode configuration, or if I draw one more diagram in which I will make my anode common. So as I said, there are 1, 2, 3, 4, 5, 6 and 7 LEDs are there, right? I will note them as like this. So this will be the, yes, I have forgot to tell you the symbol of an LED. So if I go back and come to this LED diode, so this LED diode symbol is this one, which is a normal diode with 2 arrows going out from it. It means it is emitting one. So this is the symbol. Now if I take this common anode case, it means I am going to make my anode common of all these 7 LEDs. So I will draw here 7 LEDs. 2, 3, 4, 5, 6 and 7. Now these are all the nodes of these 7, so I will make them common. Means they are all connected to a single pin. Let it be it will be connected to a positive voltage, for example, plus 5 volt. and the other ends will be connected to a resistor. These are called as this resistor is called as the limiting resistor, just to protect your LED from any damage, or just to limit the current flowing through this LED. If I directly connect it, it may damage it, because we have seen that at 0.7 or 0.3 volts, depending on the type of the material, these LEDs start conducting. So definitely when a voltage of around 5 volt will be connected, it may damage it, or the LED will got burned. So these are the different resistors. I will name these resistors as R only, and these are all LEDs, so I will have two arrows coming out from it also. Now these are the points which will be left open, and depending upon the type of the voltage we have applied, we can make this LED glow. Like if I connect them with, or name them as A, B, C, D, E, F and G. So if I connect A with a voltage which is greater than 5 volt, then definitely it will be reverse biased. Like if I take this special case over here, A, and it is already connected to plus 5 volt. Now to make this LED to glow, I need to provide a voltage difference across this diode, maybe for example equal to 0.5 volts. This is my case. So definitely this A must be less than 4.5 volts. If A is less than 4.5 volts, then only the total voltage difference from this to this, or across this resistor and this, will be 0.5 volt, and this LED will glow. But if this difference is greater than, or you can say, let me take an example, plus 5 also. If both are connected to plus 5 volt, definitely there will be no potential difference between these two, and this LED will not glow because it will not come in the forward bias case. So this is the case of common anode, where all the anodes are connected together to a high voltage, and depending upon the type of the voltage connected, or if I take the normal case, if I make this A low, then definitely this LED will start glowing. If this C is made high, high means a high voltage, this LED will not glow, right? So on we can adjust all these LEDs. So this is the case of 7 segment. And second case is the common cathode. In the common cathode, we have all the cathodes connected together. Like if I connect this, one, two, so on up to, we have here 7 LEDs again. And now over here this will be connected together. Now definitely this is the N side, it must be at low voltage, so we mostly connect it to ground, for example, just an example, or you may connect it to a low value. Now depending upon the value or the LED you want to glow, for example, if this is A, B, so on up to this is G, if I make A to be connected to the plus 5 volt, definitely there will be a difference between these two, and this LED will be forward biased and it will start glowing, right? And if I connect G with the same voltage, or for example 0 voltage, then there will be no potential difference and it will not glow. Like, so this is how we will control the LEDs in a 7 segment, and depending upon that we can have various numbers. Like if all the LEDs are glowing, then we will find 8. If only B and C will be on, then we will find 1. Or if I want 2 to glow, or I want 2 number, then 2 will be represented in the 7 segment like this. So you will find this A, B, D, E and G will be turned on and rest will be turned off. So this is how this 7 segment display works. Now last topic is the photodiode. So next I will take the case of a photodiode. Now this photodiode is nothing but a normal diode with very few changes. Like we have a diode which is denoted earlier like this. Now this is a photodiode, it means some light is going to fall on it. So I will represent here an arrow which is showing me that the light is entering on it, or in some of the books you will find one more symbol of it, like this lambda written on the below of this diode symbol. So if I take the case of a diode, in a normal diode we have seen there is nothing but a P and N junction, and we can do the forward biasing or the reverse biasing depending upon the type of the operation we want. But in the photodiode, what we do, we make this depletion region more wider. Now how to make the width of this depletion region more wider, it is important. We have already discussed the formula which I have given you in the case of a diode, that is equal to, width is equal to 2 epsilon S by Q 1 by Na plus 1 by Nd into V0. Now V0 is depending upon only the thermal voltage, so we are V0 as we seen that V0 was equal to Vt natural log of Na Nd upon Ni square. Ni is fixed for any material, Na and D is the two doping concentration, and Vt is the thermal voltage. So we can say that here that the V0 is only depending upon temperature and the doping concentration. But if we see here, this epsilon S is also constant for a material, Q is also constant. Now depending upon the type of the doping, if we are doing high doping, low doping, or moderate doping, we can adjust the width. Or if I reduce this formula, can I say now my width will be instead of equal to, I will use here, it is inversely proportional to the root of doping. It means by simply changing the doping concentration in any P and N type semiconductor, I can change the width. If I decrease the doping, definitely the width will going to increase. So here the condition for the photodiode is that the doping should be small so that the width will be large. Why we are having, we want here a more width, I will discuss this now. Now in the case of photodiode, we don't operate it in the forward bias, we operate only it in the reverse bias condition. Now why we operate it in the reverse bias? Now in the reverse bias, if we see, we already have made our width large by decreasing the doping, and by applying the reverse bias voltage, we can say that we have further increased our width. Now if this is my P side, this is my N side, P will be connected to negative and N will be connected to the positive. So we will get this diagram. Now this is my depletion width, which I have increased, one by doing the reverse biasing and second by doing the decreasing the doping of the materials, P and N type materials. Now in addition to it, now what I am going to do, I am going to have a photosensitive coating over here. It means on this depletion region I am going to add a photosensitive coating. This photosensitive coating, photosensitive coating. Now this photosensitive coating can be of any material, maybe cadmium sulfide or selenium or zinc sulfide, any material you can use for this photosensitive coating. Now due to this photosensitive coating, what is going to happen when the light is going to fall on it? As I said, it is a photosensitive, so light will fall on it. Due to the fall of the light on it, there will be the generation of electrons and holes. Now there are two cases. We have already studied the recombination process. Recombination is nothing but an electron and a hole is combined together, and when they combine, they release an energy. This is what we have seen in the case of when they release energy, we see the light is emitted in the visible or the invisible, or in the invisible spectrum, and we say this is the case in the case of LED. But now we are discussing here an opposite case. We have an electron and hole which is combined together, and we want light to fall on it in such a way that these electrons and holes will be now separated. So this reverse process is going to happen. In the LED, what is happening? An electron and hole is combining and light is emitting. This light is in the visible region or in the invisible region depending on the type of the material. But in the photodiode, we are applying here reverse biasing. We are increasing the width of the depletion region, and we have applied a photosensitive coating such that when the light falls on this material, then there will be generation of electrons and holes, and due to that, these electrons and holes, when will be generated, they will be circulated inside this because of the reverse bias. If I say electron is generated, definitely it will be it will be moved towards the positive terminal. Okay, this electron will be moved towards the positive terminal and this hole will be moved in the negative terminal. So due to that the current will flow. Now already we have studied in the reverse bias we have a current called as the leakage current, I naught, leakage current. But now in the photodiode, in addition to this leakage current, the current which is flown due to the production of these electrons and holes because of this light falling on the photosensitive coating, we have one more current which is named here as the I photon. So this I photon is the current due to these electrons and holes generated, whereas this I naught is a leakage current due to the minority carriers, which is already there because it is a combination of a p and n type semiconductor minority carriers, right? So this I photon current is always greater than the, we have seen it up, that I photon is always greater than this I naught, or in some of the books you will find it also as I dark. I dark means when no light is falling on it, there is totally dark, then definitely there will be no photon current, only leakage current will be there. So can I say that in a photodiode we have two types of currents and this both the currents are contributing, so my total current will be equal to the leakage current plus the photon current. This leakage current value is, you know, it is in microampere in germanium diode and it is in nanoampere in the case of silicon diode. Electrons are moving towards the positive terminal and holes are moving towards the negative terminal. But look here, the important thing to understand here is that these electrons and holes are very high in this region. Now electrons here, electrons are generated everywhere and holes are generated everywhere over here due to the light falling on it. Now due to this, now these electrons are now in higher concentration in this region in comparison to the electrons in the n side. And similarly, the holes in this p side are in now lesser concentration in comparison to the holes generated inside this depletion region. Due to that, now these electrons are moving from higher concentration towards the lower concentration, and due to this region, this current is called as the diffusion current. Is it clear? Although if I say that electron is moving from p side to the n side, then that is drift current. But over here the electron is not moving from the p side, it is moving from the depletion region. In the depletion region, the electron and holes are generated and they are in very large quantity in comparison to the holes of the p side and electrons of the n side. So can I say here that photodiode current is the diffusion current. And the photodiode current, total photodiode current can be written as I is equal to Is plus I naught 1 minus e to the power minus v by eta Vt. So this is the formula of the photodiode current, or the total current flowing inside it. And you can see here that this curve is the exponential curve, or 1 minus e to the power minus x curve is somewhere like this. It means it increases exponentially. Exponential increase is there in the carriers or in the current. So I guess you got an idea or the differences between a normal diode, ideal diode, light emitting diode and a photodiode. So I'll stop my lecture over here. Thank you.